So today we start the next topic in mechanics, which is the motion of extended bodies going round stuff. And I have a couple of three examples gracing the slide. And so we're going to remind ourselves what kind of coordinate we want to use to describe rotational motion. There's going to be an analogy with momentum, a new conserved quantity for isolated systems, and that will be angular momentum. And we will find out what's the analog to mass. It's a bit more complicated in rotational motion, and it's called either rotational inertia or moment of inertia, and we'll learn how to calculate that. So let me start by reminding you, these are the coordinates that we use to describe cycles. So we have an angle, often called theta, could be alpha, could be Fred. Actually, it won't be alpha because we're going to use that for something else. S would be the distance moving around the circumference of the circle, and of course, S is equal to R times the angle theta. And so the speed with which the particle moving around in a circle goes is the product R and omega, where omega is the time rate of change of that angular position theta. So we cooked up an analogy with V for rectilinear motion, omega for angular motion, and we hadn't worried in the past too much about what about that second derivative of the angular position with respect to time. And omega is about as close to V as the Greek alphabet gets, so that's that analogy. But alpha looks a lot more like an A, and that's the analogous thing to acceleration. So angular acceleration is denoted either by something like theta double dot or alpha. Okay, and we're going to use a convention that is the standard one when you're working in the plane, namely if you go around in the counterclockwise direction, that's positive. If you go around the clockwise direction, that's negative. And the time that it takes to go once around is called the period. And since there are 2 pi radians in going round, then the angular velocity, if it's constant, is just 2 pi over the period. So that should be familiar from before. Anyone see a problem with this way of describing rotational motion? In the cheap seats. It doesn't allow for a change in the radius. He says this assumes a fixed radius. So yeah, I've shown for a particular circle, but we might imagine if the radius were to change, we could still use this expression here to figure out the relationship between the new radius but which component of V? That maybe is what you're driving at. So this is only going to worry about the part of going round, not the part radially outward or inward. Exactly right. So that's a fair point. Anything more primitive? Nobody has a clock that goes backward? Yeah? Okay. So when we look at this, clockwise means that we're looking from where you are at that thing, and that means that going around this way is called clockwise. Suppose somebody were actually behind it and looking out. What would they call clockwise? It'd be backward compared to you. Yes, sir. Jesse? So so he says, yeah, well, if we have different coordinate systems, then that's going to happen. Fair point. What if instead of thinking about the motion as being confined in the plane, so this would be rotation about which axis? Z-axis coming out, right? X, Y, and then Z would be coming out of the screen. So what if that axis were to change direction? What if that floats around in space? So I want us to start without worrying about that. We'll get to that later. And so for the moment, we're going to just confine the motion to a plane around a fixed axis, but we have to anticipate that eventually we're going to have to maybe generalize a bit, because we're going to have to account for what happens if the axis is moving too. And that's what's going to make rotational motion so goofy and interesting.